generation and recombination. These are two processes that keep on happening continuously in semiconductors as long as they are at temperatures above 0 degree Kelvin. Generation refers to creation or production of free electron hole pairs. For creation of free electron hole pairs, it requires energy to be supplied to the electrons. This energy may be in the form of heat, it may be in the form of radiation, or it may be in the form of light. In case of recombination, what happens is free electron and hole joins each other, resulting in their disappearance, leaving behind a small amount of energy. This energy left behind may be in the form of heat, it may be in the form of radiation, or it may be in the form of light. One can notice during generation, free electrons come into being, holes come into being, and as a result, flow of electricity, it becomes more, conductivity becomes more. During recombination, it can also be noticed electrons, free electrons disappear, holes disappear, so carrier concentration decreases, resulting in decrease in the conductivity, resulting in decrease in the flow of electricity. Electronic devices, semiconductors, part 6, series on semiconductor devices and circuits, lecture number 1.16. Semiconductors and metals, they differ mainly in two different ways. In metals, the current is due to flow of electrons, whereas in semiconductors, in addition to electrons, whole movement also gives rise to current. Therefore, holes as well as electrons both contribute to electric current in semiconductors, whereas only electrons contribute to current in metals. Another basic difference between semiconductors and metals is that in metals, it is the drift phenomena that is responsible for the movement of carriers, electrons, whereas in addition to drift in semiconductors, there exists diffusion phenomena also. Both drift as well as diffusion play a significant role in the movement of in the flow of current carriers in semiconductors. In the present session, the focus is on transport phenomena in semiconductors in addition to mobility, generation, recombination, and various other interesting aspects. With this small introduction, now we move to begin the core session. We start the session by considering the types of recombination. There are four varieties of recombination. They are direct band-to-band recombination, indirect recombination, Auger recombination, surface recombination, and in the coming slides in this session, we discuss at length about these four types of recombinations. Here the focus is on one type of recombination. It is direct band-to-band recombination. A few points regarding this phenomena, band-to-band recombination. It is a spontaneous process. It takes place when an electron from the conduction band falls into a hole, an empty state in the valency band, releasing energy as photons at optical frequencies. It occurs in a direct band gap materials, and gallium arsenide is an example for such type of material. For this reason, direct band gap semiconductors are used for light emitting applications. In this transition, note that no change of electron momentum takes place. What is this direct band-to-band recombination? To understand this particular phenomena, consider energy band diagram of a semiconductor. At the bottom, valency band. At the top, conduction band. In the middle, band gap is there. When conduction band electron, a free electron, falls into a hole, or it falls down into valency band, then it is named as recombination. Band-to-band recombination means electron falls from conduction band to valency band directly in one step. We are going to see there are other ways of recombination too, where electron fall from conduction band to valency band is in steps, more than one. In band-to-band recombination, it is direct, a single step process. It is spontaneous. It occurs in certain type of materials like gallium arsenide. Here, in this process, there is no change of electron momentum. Indirect recombination. It happens in indirect band gap materials like silicon and germanium, with the help of a third party called recombination centers, which are actually defect states that lie in the middle of energy band gap. Energy released during these processes is carried away by phonons. Band-to-band recombination releases energy in the form of photons, but here it is released in the form of phonons. The phonon frequency is not in visible or infrared region, and maximum it can vibrate the lattice. These are not suitable for optoelectronic applications. To understand indirect recombination, you consider once again energy band diagram of a semiconductor. Conduction band, valency band, band gap. In indirect recombination process, what happens is a conduction band electron, it falls into a valency band not in a single step. It occurs in 2 or more steps. In the first step, conduction band electron falls to a level that is within band gap, somewhere here. The electron stays in that state for some time and then it falls into valency band. So it is a 2-step process. Conduction band to valency band transition is a 2-step process. It can be 3 steps also, but it is not a single step, hence it is not direct band to band. For this reason, it is termed as indirect recombination. Recombination is always associated with release of energy. In indirect recombination, energy released is small when compared to energy released when recombination is direct band to band. As energy is released, the frequency of that particular energy is also small because energy is related to frequency through Planck's law, E equal to hf. Low energy means low frequency. That low frequency energy, it is carried away by phonons. These are not suitable for optoelectronic applications. Optoelectronic applications are applications which are associated with light. Light means very high frequency. But indirect recombination is associated with low frequencies. So therefore this phenomena cannot handle optoelectronic applications. Another type of recombination is also in existence. It is called Auger recombination. It can happen only in heavily doped direct bandgap materials, and during recombination, the released energy is transferred to a hole in p-type materials and to an electron in n-type materials. During this process, no EM radiation is emitted as released energy is absorbed by another carrier, raising itself to a higher level in its respective band. Surface recombination is another type of recombination. It takes place near the surface of semiconductor device. It is due to presence of extra defects and trap states at the surface. Before going further, it requires to be mentioned that in a semiconductor slab, as long as it is at above 0 degree Kelvin, 2 phenomena continues to happen without any break inside the slab. What are they? One is generation, another is recombination. During generation, an electron takes energy, comes out of the covalent bond, thereby generating a electron hole pair. So generation requires energy supply from outside. After being generated, this electron hole pair travel in a random manner. They move certain distances. They spend some time as individual particles, and then they encounter oppositely charged particles to get recombined. During recombination, electron meets hole or hole meets electron, and both particles disappear, leaving behind certain amount of energy, releasing certain amount of energy into the outside world or into the crystal structure. So generation requires supply of energy, recombination releases energy out. A few points regarding thermistors. Thermistors, these are devices semiconductor devices, the functioning of these devices is based on a property of semiconductors. What is that property? Conductivity of semiconductors. They have the nature of varying conductivity with temperature. This property is used in the design of devices, thermistors, and also sensistors. The conductivity of silicon, germanium 2, is found to increase at a rate of approximately 8%. 8% in case of silicon, 6% in case of germanium, per degree increase in temperature. Such a large change in conductivity with the temperature places a limitation upon the use of semiconductor devices in certain applications. It is a shortcoming. Changing conductivity with the temperature is basically a shortcoming. In fact, this is considered the biggest disadvantage, a shortcoming, as far as semiconductor devices are concerned. However, there exist certain applications which use exactly this property for advantage. The semiconductor used for this property, it is called thermistor. These devices find applications widely in the measurement of temperature, microwave power, and they are also used as thermal relays and thermal control devices. Some more points regarding thermistors. The commercial thermistors use sintered mixture of such oxides as nickel oxide, manganese oxide, and also CO2, O3. Silicon and germanium are not used for thermistors because their sensitivity to impurities. Note that a heavily doped semiconductor acquires the properties of a metal and its resistance increases. When doping is normal, semiconductor's resistance decreases with increase in temperature because conductivity increases with the temperature. But when doping is heavy, huge, then resistance increases with temperature, with the temperature exhibiting a positive temperature quotient of resistance. Semiconductor devices that are made to use this property, they are called sensistors. So thermistors use the property of increase in conductivity with the temperature, whereas sensistors use the property of decrease in conductivity with increase in temperature. The first property gets manifested when doping is normal. The second property gets manifested in semiconductors when the doping is heavy. Some more points regarding photoconductors, semiconductor-based devices. Conductivity of semiconductor is varied by radiation, by irradiating the semiconductor slab. The radiant energy incident over the semiconductor energizes the valence electrons to become free, thereby generating free electron hole pairs. Notice basic requirement to generate electron hole pair is supply of energy to the electron that is in the covalent bond. This supply can be in any form. It can be in the form of heat. It can be in the form of light. It can be in the form of some electromagnetic wave, radiation. It can be anything. So as far as photoconductors are concerned, their functioning is based on supplying energy to the electron in the covalent bond through radiation. Once sufficient energy is available to the electron, it comes out of the covalent bond, thereby generating electron hole pair. Increase in carrier concentration leads to increase in conductivity or decrease in resistivity. The devices that use this principle, changing resistance with irradiation, these are called photoresistors or photoconductors. So thermistors, sensistors, photoconductors, these are all devices which function on the principle of changing conductivity, varying conductivity of semiconductors by changing new electron hole pairs, by supplying energy, thermal energy, or by supplying radiation energy. Now, some points regarding carrier transport. As already mentioned, there exist two types of carriers in semiconductors, electrons and holes. And also it is mentioned that there exist two types of phenomena that cause current in semiconductors. So one is a drift, another is a diffusion. Now we spend some time here in understanding the phenomena of drift and diffusion. Transport in semiconductor happens through drift and diffusion. What is drift? Free electrons and holes move under the influence of applied potential gradient due to Coulomb's force. That is drift. So drift is current flow movement of charge carriers under the influence of potential gradient. Diffusion, a natural tendency for free electrons and holes move from more concentration regions to low concentration regions whenever there is a concentration gradient. This phenomena is called diffusion. To understand, consider a slab. Let us say it is N-type slab, plenty of electrons inside. If you connect a voltage source like this, electrons are there inside, so these electrons get attracted towards positive terminal. So flow is there. This flow of electrons is due to attractive force that exists between positive terminal of the battery and negatively charged electrons. So it is the voltage source that is causing the current. This current is called a drift current. This process is called a drift. So electron movement is due to applied potential. Then what is diffusion? Let us suppose here is a semiconductor slab, let us say N-type. Now, by one means or other, let us say, plenty of electrons are injected from one end. So in this end, there exists lot of electrons. Electron concentration, therefore, here at this end is very high when compared to electron concentration at the other end. Therefore, one can easily notice there exists concentration gradient along the length of the slab. There's a difference in concentration levels as we move along the length of the slab. Natural tendency, it is natural phenomena. Diffusion happens for electrons from high concentration regions to low concentration regions. They just move. It is a natural phenomena. This phenomena is called diffusion. So diffusion is another phenomena that cause movement of carriers. Notice, whatever may be the cause, it can be drift, it can be diffusion, movement of carriers happens, and this movement leads to existence of current, electric current. So in semiconductors, drift current exists, diffusion current exists. There are two parameters that describe and determine mathematically the carrier transport in semiconductors. One is mobility, symbol is mu. Other is diffusion constant D. First one pertains to drift and second one belongs to diffusion. Each type of carriers, electrons and holes, has its own values for these two parameters. Mobility is a parameter that pertains to drift, whereas diffusion constant pertains to diffusion. And mobility for electrons is different from mobility for holes. Similarly, diffusion constant D for electrons is different from diffusion constant for holes. A few points regarding mobility. Consider a conductor, a semiconductor, and under the influence of an externally applied field E. Charge carriers then drift with certain velocity Vd. Hence, one can write Vd, drift velocity, is equal to plus or minus mu, some proportionality constant, multiplied by E. What is this E? Consider a slab, apply voltage. Let us say this voltage is V. Voltage is also called potential. Now, if length of the slab is L, V by L, V by L. V is a potential, L is length, V by L is called potential gradient. This is nothing but field intensity, electric field intensity. So electric field intensity or potential gradient, it comes into the slab when a source, voltage source is connected. Under the influence of voltage source, potential gradient comes into being inside the slab. Electrons move towards positive terminal because of attraction. Holes move towards negative terminal for the same reason. Notice this movement is not in straight lines, either electron movement or hole movement. It is not in lines, in straight lines. The movement is not like this. The movement is random. It moves like this, like this, like this, like this, like this, like this, like this. And slowly, while having this random movement, under the influence of potential gradient, the electrons drift towards positive terminal, holes drift towards negative terminal. The velocity with which they drift, that velocity is indicated by Vd. It is proportional to potential gradient. Mu is proportionality constant, plus minus 1 for electrons, 1 for holes. Here mu is proportionality constant with units meter square by volt second, known as mobility of the carriers. Electrons are holes. The sign plus in case of holes and sign minus in case of electrons. Electrons and holes have different values of mobility, and in general they are functions of effective mass as well as the mean distance the carrier moves in between collisions. The carrier transport is further illustrated in this slide A. Acceleration of particles in free space. You consider an electron in free space, not in semiconductor, in free space, in between two plates. One plate is at positive voltage when compared to other. So Coulomb's force comes into being, and this force imparts acceleration to the particle. Because of this acceleration, the particle moves towards positive plate. The acceleration can be found equal to E, charge on the electron. E means potential gradient. Me stands for effective mass. Similarly, holes. Hole move towards negative plate. This is the situation when electrons and holes are in free space. Now we consider the situation where electrons and holes are in crystal lattice. Now it is not free space, it is a crystal lattice. When electron or hole is in crystal lattice and they are moving, they encounter collisions between atoms of the crystal lattice and also particles, charged particles, electrons and holes, other electrons and holes. As a result of these collisions, what happens is the path of electron or hole becomes quite random. Here we considered an electron. You see, this electron is first moving and colliding with an atom. Then it is moving towards another atom, colliding. another collision, another collision, another collision. These collisions lead to the movement of electrons and also holes in random paths. This is the situation when there is no applied voltage across its terminals of the semiconductor slab. This movement is due to thermal energies available in the lattice. Now, when voltage is applied, left side it is positive, right side it is negative. Now, in addition to the random movement, electrons and holes, they also possess certain amount of drift. This drift is towards positive terminal for electron, negative terminal for hole. The velocity with which it drifts is drift velocity. Going further, it is to be mentioned that the total velocity of electron consists of two components. For holes also two components. One is drift velocity, another is thermal velocity. Thermal velocities are very high. Thermal velocity means the velocity with which the electron moves between two collisions or hole moves between two collisions. Let us say here to here. In this diagram, the legion is given here. Symbols for electrons, holes, acceleration, drift velocity, all that is explained. After drift, a few points regarding diffusion. Rigorous mathematical analysis says the diffusion length square is proportional to mean life period. Mathematically, L bar square is equal to D tau bar. Here the proportionality constant D with units of meter square per second is diffusion constant. Usually the electrons and holes in a semiconductor have different diffusion constants. As already mentioned, they are indicated by D and dP. Now, a few points regarding L and tau. What is L? What is tau? After generation, an electron or a hole also, electron keep on traveling. While traveling, it encounters a hole and recombination happens, resulting in its disappearance. From generation to recombination, an electron travels a certain amount of distance. That distance is diffusion length. Individual electrons, individual holes, they have their own individual diffusion lengths, different lengths. Individual diffusion lengths are not that much important, but average diffusion length is an important parameter in semiconductor physics. L bar indicates average diffusion length. Now, what is tau bar? From generation to recombination, from birth to death, there exists certain duration. That duration varies from electron to electron, from hole to hole. Individual electrons' lifetime is not important, but average, its average is quite an important parameter. Tau bar indicates average lifetime or mean life period. Here D is proportionality constant. Proportionality constant between L bar square and tau bar. There is one important relationship. We use this relationship very frequently. It is called Einstein relationship. It relates the diffusion constant to mobility ratio of carriers. dP by mu p, diffusion constant pertaining to holes. That is dP. Mu p means mobility pertaining to holes. So dP by mu p. It is equal to dN by mu n. Here D and mu pertains to electrons. It can be shown that this ratio is equal to Kt, Boltzmann's constant K. T is temperature. And substituting the value of K in this expression, it can be shown the ratio as T in Kelvin scale divided by 11,600. This ratio is usually indicated by Vt. Vt is 26 millivolts at room temperature. At room temperature, T is 300 degree Kelvin, 300 degrees. If you substitute, we will be getting 26 millivolts. Vt is called volt equivalent of temperature. Now in this slide, properties of commonly used semiconductors like silicon, germanium, gallium arsenide at room temperature are given. Atomic number, atomic weight, density, dielectric constant, atoms per cm cube, band gap in electron volts, intrinsic carrier concentration, electron mobility, hole mobility, electron diffusion constant, hole diffusion constant. These are all important parameters. One has to be well versed with the values of these parameters if one wants to have a grip over the subject electronic semiconductor devices. With this, we come to the end of the session. Let us recollect briefly the important areas which we touched upon in this session. Mainly, it is about transport phenomena in semiconductors, drift phenomena, diffusion phenomena, mobility, diffusion constant, and in addition, we also described different types of recombination processes that are there. Enough for now. We meet again in another session with a new topic soon.